Hello, my dear students. Welcome to the next subtopic of semiconductor chapter. And in this subtopic, we are going to learn the working of a bipolar junction transistor as an amplifier. So, in the previous session, while learning the output characteristics of bipolar junction transistor, we understood that the transistor can be operated in three regions. The first is cutoff region, the second is active region, and the third one is saturation region. In cutoff region, the transistor can be used as an off switch, while in the saturation region, the transistor can be used as an on switch, while in active region, the transistor can be used as an amplifier. The transistor as a switch is not present in your syllabus, it is not included in your syllabus. You can say that we'll be learning the only one application of the transistor, that is the working of the transistor as an amplifier. So amplification means if suppose this is the input signal, this is the weak signal, I can say this is the input signal, which is of only 5 millivolt in magnitude, peak to peak. This is plus 5 millivolt, this is minus 5 millivolt. And if suppose the output we are getting is the amplified one means the frequency will remain same, but the amplitude is going to increase. Suppose it is directly made to plus 2 volts and minus 2 volts. Okay, so from millivolt it is getting converted into volts. So that means we are actually amplifying the signal. So this is the input signal, this is the output signal. I can say it has passed, the input might have passed through an amplifier. The input has passed through an amplifier so that its amplitude is amplified, it is increased by some particular factor. So we are going to learn about the working of the transistor, how this transistor can be used as an amplifier. So amplifier, it is a device which is used to increase the amplitude of alternating signal. Alternating signal means AC supply, right? It can be current, AC current, it can be AC voltage, or it can be AC power. So amplifier, it is used to amplify the, or I can say increase the amplitude of alternating signal in the format of voltage or current or power. This is the circuit diagram available in the textbook. This is the circuit diagram given in the textbook. I can say that I will explain you the circuit diagram. This is the transistor part. We all know this is the transistor part. So this is denoted by Q, and this is the NPN transistor. Why? Because the anode is towards the emitter side, right? Moving to the input side, this part is in the input side of the transistor, while this part is on the output side of the transistor. So we'll be learning first the input side of the transistor. This is the voltage VBB. Okay, so please note this. This is not VBE. This is the voltage VBB. So this is, we require a variable voltage. So in order to supply to the base, I can say this is the VBB voltage and this is the VCC voltage, not VCE voltage. This is the VCC voltage. Okay, all of you please do the correction. There is a lot of correction in the textbook. So this is the VCC and this is the VBB. So VBB, through VBB there will be a constant amount of current, it will be flowing through the base. Okay, such that this is the NPN transistor. I can say this is the P type. P, it is connected to positive terminal of the battery. This is the N type and it is connected to the negative terminal of the battery. So this junction, it is forward bias. So we want the input to be forward bias and output to be reverse bias. So in order to reverse bias the output, this is N, which is connected to positive terminal, and this is again N, I can say this is connected to negative terminal, right? So this is actually in the reverse bias condition. Okay, this is actually in the reverse bias condition, right? Now this is the common emitter configuration because the emitter is connected to ground. We want alternating supply like this. So this is the input signal which will be giving you the alternating voltage. So this is the V in, which is giving you the alternating voltage AC. This capacitor, it is used to remove the DC component. Capacitor capacitor is used to remove DC component. Capacitor is used to remove the DC component. Okay, this is the RB. RB, it is the uh, base resistance. This value is very less. This value is very less. Why? Because there is a very less amount of current flowing to the base, which is in the microampere. So that's why this RB value has to be very less. If it is more, then this microampere will be actually converted into nanoampere because of the resistance. So we don't want this thing to happen. That's why the RB value, it is considered to be very less. So I hope you understood the input side. I will erase this thing. You are requested to please pause the video. You can draw the circuit diagram, okay, a big circuit diagram, and you can note these things which I am drawing on the circuit diagram. Okay, it will be very helpful for you to understand visually by just by looking at on the circuit diagram. And after that, if you read the theory of the circuit diagram, you will understand each and every point in detail. Okay, so I can say this is the VBB, this is the VCC. Okay, and if suppose I want to measure the voltage across BE, so this is positive and this is negative. I can say this is VBE, the voltage across VBE. So it can be measured by connecting a voltmeter which is parallel to this, not parallel to this, just like the input characteristics we have seen. But in order to avoid the complication in the circuit, we will write this plus minus VBE like this. Okay, and there's no resistance present in the IE branch. So IE is directly connected to ground. So that means no current flows through this branch because it is directly connected to ground. No voltage drop is there because it is directly connected to ground. Zero voltage drop is there. Okay. Now I can say we'll talk about the output side now. So if I talk about the output side, this is not the source. This is not source. This is not source. This is the source. Source means it is going to supply the alternating voltage. This is used to measure. This is the measuring device. This is the measuring device. Okay, that means it is going to measure how much is the voltage present at this VO. So what is the transistor part is, if suppose I consider this is the amount of input voltage, the output voltage will be getting like this. So the amplified version will get, but the inverted form, it will be measured in the inverted form. So if suppose the transistor it is used as an amplifier, the input waveform it will be inverted actually like this in the reverse form. This is the measuring device. I can say this can be an oscilloscope in on which we can actually measure the waveforms. Okay. So this is again the capacitor is there. So capacitor is used to remove the DC component. Capacitor is used to remove DC component. Okay, this is the load resistance connected, load resistance connected like this. So amount of current flowing here is IC. So this is the IC because this is the measuring device. No current will be moving in this direction. So this is the IC part. IC current will be flowing to the collector, and this is the IB current which is flowing to the base, and this is the total amount of current will be flowing to the emitter branch. That emitter current is equal to base current plus collector current. Okay. So I hope all of you have understood this circuit diagram. Okay. Now, why we are getting this inverted output, we will be learning in the last slide of this transistor and amplifier subtopic. Okay, I'm moving to the next slide. You can pause the video. You can write the things, draw the circuit diagram. Okay. So it is a measuring device. For example, it can be called as oscilloscope. So this can be oscilloscope. Okay. So what is the working of the transistor as an amplifier? We'll be considering the output side, and after that we'll be considering the input side. We will write the equations of both sides. Okay. So first I am considering the output side because the output side is easy. So this is the VCC branch actually, VCC voltage. Okay. And this is actually this, you can say it is an open circuit. Open means it is like this. It is like this. Open it is. So openly we can measure the value of VO. Okay. So whatever is the VCE value, VCE value, it is actually the value of VA. Okay. Whatever is the plus minus VCE, the same we will be getting, we were talking about VBE. This is the plus minus VCE branch. Okay. So let us now consider the output side. I will again draw neatly. This is the VCC value. This is plus minus VCE value. Okay. Now I will be applying KVL to this loop. So suppose I apply KVL to this loop like this, I will be applying KVL to this loop like this. What I will getting? Kirchhoff's voltage law. So if I apply Kirchhoff's voltage law, so first this is suppose named as A, B, C, D, A. So this is what A, B, C, D, A. So first is AB branch. So we'll be looking at AB branch. To this AV branch, we are actually moving towards the positive terminal of the battery. So I can say it is plus VCC because it is moving. We are moving towards the positive terminal of the battery. From A to B, we are moving towards the positive terminal of the battery. That's why it is plus VCE. Now the current flowing is this, and also we are moving in the same direction as that of the current. So we have to consider the negative sign. So this is the sign conventions of Kirchhoff's voltage law. But suppose we are moving in the direction A to B, and the current is also moving in the same direction, then we have to consider negative sign. Negative voltage across this RL, and as per the Ohm's law, voltage is equal to current multiplied by resistance. So the resistance is RL, the current is IC. So I can say it is IC into RL, IC into RL. Again, from B to C, there is no resistance is present, no voltage is present, so we will not write anything. Now from C to E, there is one voltage present. It is from plus minus VCE. So from moving towards from C to D, moving towards C from C towards D, we are actually moving towards the negative terminal of this VCE. So I will write minus of VCE, minus of VCE. Again, the last one is DA. So if moving from D to A, there is nothing is there, so I will not write anything. Now since it is completely closed, we have started from A and we have ended at A. So I can say the summation of all these things it is equal to 0. The summation of all these things is equal to 0. So therefore what I can write? I can write VCC that is equal to ICRL plus VCE. VCC it is equal to ICRL plus VCE. Okay, so we are applying KVL, that is the Kirchhoff voltage law, to the output loop. So we'll consider the output loop AB, CDA. So considering this output loop ABCDA, so this is the equation we are getting actually. VCC is equal to ICRL plus VC. Okay, you please pause the video. You can write the things. I'm going to the next slide, that is the input side. So if I consider the input side of the transistor, so the input side looks like this. I will write like this. This is the VBB, and this is plus minus VBE. This is the plus minus VBE. So again, if I suppose apply Kirchhoff's voltage law to the input side like this, this is suppose PQ R. I will not write this as R. Okay, let it be PQRST. Okay, so I will write like this, applying KVL to PQRSTP. Again, the first and the last one should be said, so that you can say it is the closed circuit, closed loop, closed mesh. So that KVL it is applicable for only closed mesh or closed circuits. The first is PQ. So moving from P to Q, I am actually moving towards the positive terminal of the plate. So it is plus VBB plus VBB. Then from P to Q to R. Q to R, actually we are moving in the direction of the current. So since we are moving in the direction of current, I can say it is minus of IB RB, minus of RB IB RB. Then from R to S. From R to S, actually we are moving towards the negative terminal of VBE. So I can write minus of VBE, and then TP. TP and ST. ST and TP, nothing is there. No, none of the branch contain voltage source or it contain a resistor. So I can say the voltage drop across this branch is zero. So summation of all these things, we have started from P and we are ended at P. So the summation of all these things that is equal to zero. So what I can write VBB, it is equal to IBRB plus VBE. VBB it is equal to IBRB plus VBE. Okay, so this is the VBB value if V in is not considered. If V in is not considered, so we'll say applying KVL to the input loop. Input loop it is PQRSTP. Now we are not considering the V in value. Okay, that means without V in. I can write VBB it is equal to IBRB plus VBE. So VBB it is equal to IBRB plus VBE. Now what if I consider this VIN? Now VIN it is nothing but the variable, the change in voltage. So change in voltage will result into change in current. So this will change the current through IB. So I can say this is change in current IB multiplied by the voltage is equal to current multiplied by resistance. Resistance here it is RB. So it will be RB plus the next resistance will be the dynamic input resistance that we have already studied in the input characteristics of the transistor. Dynamic input resistance it is nothing but denoted by Ri. Okay. Now in the circuit diagram, while explaining the circuit diagram, I told you this RB value is very small. It is very small such that it can be neglected. So if you neglect this, what will be the value of V in will be getting? V in will be getting as delta IB. RB we have neglected, it will be multiplied by small Ri. Okay, so this is the value of V in. I hope you are getting the things. You can pause the video, you can again watch the video if you want. Expression of V in. Expression of V in. So V in actually it is equal to actually it is equal to delta IB into RB plus RI. But RB is very small. So therefore I can neglect this RB and I can write V in it is equal to delta IB into R. Okay. So all of you please pause the video. You can write the input consideration, right? And I am moving to the final slide. The final slide is nothing but the derivation, or I can say the expression for a voltage gain. So expression for voltage gain it is denoted by AV. So this is AV, and voltage gain is nothing but the ratio of output voltage divided by input voltage. Ratio of output voltage divided by input voltage. So the changes in the base current, that means what IB, cause the changes in the collector current, which is nothing but IC. So if suppose what we are having is V in, so V in is changing, that means what is changing? Delta IB. So delta IB is changing, that means what is changing? Delta IC is changing. Okay. So V in change, that means IB is changing, IB is changing, that means IC is changing. So if suppose this part is changing, so this changes the voltage drop across the load resistance because VCC is the constant. So VCC, this is always constant. In the transistor VCC and VBB, it is always constant because these are the external power supply and these values are actually constant throughout. So what we can write therefore the output equation becomes. So what was the output equation actually? If you remember the output equation was this VCC it is equal to ICRL plus VCE. Now IB is changing because of the changes in IB, IC is changing. Okay, so that will be represented by delta IC. Okay, so let us see. So that means delta ICC plus delta ICRL plus delta VCE. This value is equal to 0. What was the output equation? If you remember, the output equation was VCC it is equal to ICRL plus VCE. Now input is changing, that will change the base current and this is going to change the delta IC. So whole thing has to be written in the changes form. So delta represents changes. So changes in VCC will be resulting into the changes in IC and will be resulting into the changes in VCE. But VCC is the constant part. So VCC is the constant part. That means the changes in VCC it will be equal to zero. Changes in VCC it is equal to zero. That's why this delta VCC, that means changes in VCC, it is actually equal to zero. Okay. So therefore, what I can write? I can write delta IC RL is equal to minus VCE. So I can write delta VCE it is equal to minus of delta IC RL. So therefore, delta VCE it is equal to minus of delta IC RL. Now we'll consider the changes in the output voltage. That means the delta VCE. Delta VCE is actually present in the output side. If you remember the circuit diagram, if you remember the circuit diagram was like this. The transistor side was like this. C, E, and this was base. This was the output side, and plus minus VCE. It was there on the output side. So the change in the output voltage, that means nothing but delta VCE is the output voltage. The changes in the output voltage, which is nothing but VO. So I told you let it be like this, and this is what VO. So that means VO it is actually equal to VCE. So VO, which is actually equal to delta VCE, the changes in the VCE value, it is nothing but replicated in the output voltage. It is nothing but minus of delta IC into RL. So delta VCE it is equal to minus of delta IC into RL. So I can say VO it is equal to minus of delta IC into RL. But we know some amplification factor, the current amplification factor called as beta. So if you remember the beta equation, the beta AC it is nothing but the changes in the collector current divided by changes in the base current. You have studied beta DC. So since it was direct current, I can write like this: IC divided by IB. IC, capital I represent the DC collector current. Capital IB represent the DC base current. But if suppose it is denoted by small I, it is nothing but the changing AC current. Small I represent AC current. Okay, so what will be the value of delta beta AC? Beta AC value will be nothing but IC divided by IB, because this is now the changing collector current and this is nothing but the changing base current, alternating base current, alternating collector current. Now this alternating change in IC it is denoted by delta IC. This can be written as delta IC and this can be written as delta IC. Okay, so these are the things. That's why I can say beta AC it is nothing but IC divided by IB, which is nothing but you can say it is delta IC divided by IB. Okay. Therefore, what I can get, I can write delta IC is equal to, I can write delta IC is equal to beta AC multiplied by delta IB. Beta AC multiplied by delta IB. So this is the value of delta VCE we already understood. So what delta VCE will be equal to? Delta VCE will be equal to, instead of delta IC, I can write beta AC IB, delta IC. So therefore, delta VCE, what it is equal to? Delta VCE is equal to minus of delta ICRL. And delta ICRL it is written here. What is the value of delta IC? Beta AC into delta IC. Minus of beta AC into delta IB into RL. This is the value of delta VCE. Now we are going to define the voltage gain factor. It is denoted by AV. So your question was to have an expression for voltage gain in the case of transistor working as an amplifier. So now we are going to define the voltage gain. What is voltage gain? It is output voltage divided by input voltage. So AV it is nothing but output voltage divided by input voltage. It is nothing but equal to, now this VO you can write it as delta VCE, right? And what is the value of VI, the input voltage? It is delta IBR. So if you remember the previous slide, the input side, if you consider, so this V in C, what is the value of V in? V in it is equal to delta IB into RL. Right? So that's why we have written V in it is equal to delta IB into RL. Now what is the value of delta VCE? Delta VCE value we have understood here. So this is minus delta AC into delta IB into RL divided by delta IB into RL. Delta IB will get cancelled. So this is the final expression for AV, that is the voltage gain. So voltage gain, it is nothing but the negative of beta AC into RL divided by RL. Okay. So the negative sign indicates that whatever is the input and output, actually it is 180-degree out of phase. Negative sign indicates input and output are 180-degree out of phase. That means if suppose the input is like this, the output it will be like this. It will be 180-degree out of phase. That means the output is inverted of the input. Okay, so that's why this negative sign indicates this, right? So we were in the we were not in the clue that how this is possible that the input and output are inverted of each other. It is because of the negative sign that we are getting here. So because of the minus beta AC, it is minus of beta AC into RL divided by RI. The input and output are actually out of phase. The next is the, if suppose they ask you the power factor, the power gain. So the power gain, it is defined as AP. Power gain, it is defined as AP. So AP, it is nothing but one more time this beta AC, it will be multiplied by AD. So what is going to be the final expression? The final expression, it will be like this. It is nothing but minus of beta AC and AD value we have to substitute. So beta AC, it will be 2 times, so it will be beta AC square into RL divided by RL. So this is the final formula for average power, and this is the final formula for average voltage. Okay. So all of you, please pause the video. You have to write these things carefully because all the things are written wrong in the textbook. So please be careful in this. Okay. So this is the topic completed. The next topic that we are going to learn is the logic gates. Okay. So the transistor, the working of the transistor as amplifier is completed. All the complete subtopic of the transistor is completed. The next topic that we are going to learn is the working of the logic gates. What are logic gates and how we can use this. This is very important topic. The logic gate are also the very simplest form in the semiconductor chapter. Thank you so much all of you for paying attention. Keep learning, keep smiling. Goodbye.